Okay, hello and welcome to my first lecture for this differential equations class. So let's just jump right into it. What are we going to do in this class? Well, it's in the name. So in this class, we study differential equations. If you can guess by the title of the class. But of course, you don't know what this means yet. So we need to know what differential equations are. And before that, you sort of have to review some stuff. So to understand this, it requires that we sort of go back in time and remember some calculus. Okay, so let's talk about that for a little bit first. We'll sort of work up to what a differential equation is. So in calculus and also like pre-calculus for now, you spend a lot of time studying things like this. Things like f of x equals, I don't know, 3x squared plus 7. So you see this kind of stuff a lot. Or you might see it written like this instead. And these are called functions. These are examples of functions. And then less commonly, you might study, but you should study this at some point. You study something like this instead. That look very similar, but they're not the same. So something like that. And this is not a function. It's a relation. But in both situations, what we do a lot is we graph things. And both of these have graphs that you can draw. So I won't do that for now, but just keep that in mind. Okay, so you study things like this. So now let's focus just on one example. So given a function, and I'm just going to write a different one this time. Something like that. Why do we also write this other thing instead? So why do we do both? What's the difference? Well, they're just saying the same thing in different ways, depending on how you want to look at things. So what we do is we graph the xy coordinates that come from the function and so that's why people write this. It's because they want to graph xy coordinates, and the y coordinates are just what comes out of the function whenever you plug in an x. And then they say things like this. There's lots of different ways to say the same thing. So you might say something like y depends on x when you're graphing it, because what you're doing is you're first plugging in a number for x, and then out pops a y after that. So y is dependent on x. Or you could just say, or y is a function of x. And that's really saying like, okay, you have a function defined by this formula, 2x squared minus 1, and the y values are the outputs of the function. So you might say that y is a function of x also. And the whole point is that when you plug in an x, you uniquely determine a y. So x values uniquely determine y values. So if I graph this one here, just as a reminder, so this is a parabola. It's going to look something like this. 1, 1, 2, 7, something like that on that side. And then it's symmetric. It's going to look the same on the other side. So it's a function because if I plug an x value in, it only turns into one y value. And that always happens. Any x value I pick just turns into one y value. Whereas a relation, that doesn't happen. And they're important too, but we don't study them as much. Whereas something like this, you might remember that this graphs a circle if you graph it. But the point right now is that it's not a function. Y is not a function of x. And you do study these things, just not as commonly. And you can see that it's not a function when you look at the graph. So this radius is 5 here, so this would be like 5, 0. But the reason it's not a function is if I plug in an x value, it does not uniquely get sent to a y value, it gets sent to 2. So you can't just say it automatically goes to 1 for sure. So here, plugging in x does not uniquely, meaning doesn't pick 1, determine a y value. So you would never write like f of x there, whereas up here you could, because the y values are functions of x, whereas you wouldn't do that here. So that's why sometimes you can replace y with f of x and sometimes you can't. That's what's going on there. Okay, so that's calculus and that's pre-calculus stuff. So then jumping into calculus next, what do you do with this stuff in calculus? Well, in calculus, you're either given a function or a relation. And then you want to do this cool thing. So let's just start with the function. So given a function like, change it up again, how about just 2x squared? Given a function like this, we want to find, the whole point of that class is you want to find the rate of change of the function. But since you could call it y equals 2x squared, you might say or of y. And the whole point of that is what that means is you want to know how much the function or the y goes up or down per how much it goes left and right. But that's can be thought of in terms of x's and y's. So you could just think about it as how much does it change in the y direction per the change in the x direction. So then the point of that class is like, well, if it's a straight line, it's very easy. That's just the slope. You could see exactly, you can just count. Okay, if it goes over 1, then it goes up 3. And then you would say like 3 over 1 is my slope. But then if you have a fancier function that creates a fancier graph, like a parabola, it's not so straightforward because it's not a straight line, and it differs. And you want to think like, how fast is it going up right there? But over here, it's going up even faster. And down here, it's going up a little bit slower. So to figure all that stuff out, you learn about something called the derivative. And that's what the rate of change is. So the derivative of y, and then you might say, because x is the dependent variable, people often say with respect to x, the derivative of y, so how much y is changing with respect to how much x is changing, tells you this. Oops. And then you learn a bunch of rules to compute derivatives. So you learn these rules to compute derivatives of functions. Derivatives. So just to remind you, I'm not going to do all the rules, but you might have to go review some. So for example, if I know my function is 2x squared, then I know this fancy rule that says the derivative is called f prime of x, and all I have to do is I have to bring that 2 down and multiply, and then subtract 1 from the power. But if I use this y notation instead, then I would call it y prime, but I could also call it dy dx. And then it would still be 4x. So there's just 2 different notations for the same thing, well, really 3 different notations. But what is this really saying? So you probably were really good at calculating and using these rules, but what is this really saying? Well, it says, for example, that when x equals 1, the derivative is 4 times 1 is 4, and you could also do it this way. But what that's saying is that if I look at the graph of this 2x squared function, so it looks something like this, and I go to x equals 1, then how fast the graph is going up, which is the also called the slope of the tangent line, this slope will have slope 4. But then if I plug in x equals 2, then the derivative is 4 times 2 is 8. So if I go out to 2 comma, that would be 2 comma 8. If I go out to 2 comma 8, then the function is the rate of change is even faster. It's 8, and that just means that the slope is even higher of this tangent line. So it's increasing much faster. And if I plugged in like -2, I would get -4, and that would tell me that it's going down at -1 at the same rate that it's going up over at 1. So that's how you like interpret the derivative in a couple different ways. So then the whole point of, not the whole point, but a bunch of the stuff you do in calculus is you're just given a function. It's got a bunch of crap with x in it. And then you use a rule to find this. And then this will only have x stuff in it too. So, and then you might call it y prime instead, or you might call it f prime of x. And it's just how fast the function is going up or down. And if you plug in a particular x value to that derivative, then it tells you in particular how fast the function is going up or down in that exact x coordinate. Okay. So then when you grow up a little bit, you learn about relations. So given relation instead of a function, you have to do a little bit, you have to think a little bit differently. So you still find the derivative of y with respect to x, but it's not exactly the same because y is not a function of x. So then we use this tool called implicit differentiation. So you may remember this, differentiation. And so what you do is you think of your derivative as something that to like apply to the equation. So you do this d dx business to both sides of the equation. And I'm not going to review all the derivative stuff with you, so you should do that on your own. But I'll just remind you of what happens. Well, the derivative of a constant is 0, so that side will be 0. Over here, when the variables match, you just do your usual rule. So derivative of x is x squared is 2x. But then when the variables don't match, you do the usual rule, but then you have to multiply by, because of the chain rule, dy dx. And then you can still find dy dx by now solving for it algebraically. So if I just subtract the 2x over and then divide the 2y, I'll have solved for dy dx. And so although y is not a function of x, we can still figure out how much y is changing as x changes. But now it doesn't just depend on x. So how much it goes up or down, y changes per how much it goes left or right. Now it depends not just on x, but x and y. Oops, I dropped the negative. There it is. So we can see this if we just draw the picture of the thing we started with. So up here, this is a circle of radius 3 centered at the origin. So I'll try to draw a good circle. And so what this is saying is how fast the y is going up or down doesn't just depend on the x value you plug in. It also depends on the y value that you plug in. And then, so like this one will have the same x value as the other one, but the y value will be down here instead. Okay, so the point is that you can still find how fast, how much the y values are changing with respect to how much the x values are changing using implicit differentiation, even though you're not starting with a function. Okay, good. So then I think that's all the review we need to now figure out differential equations. So the key takeaway is calculus, you find dy dx. Now we do the opposite of that. Sort of the opposite, put it in quotes, not exactly the opposite. So a differential equation, I'm just going to call it a DE often because I'm too lazy to write the whole thing, is just an equation that contains variables like x and y, but it could also have more variables and derivatives. So it could also have second and third, fourth, and however many derivatives you want. I just talked about first derivatives for right now. So it's an equation that contains these. And then to solve, that's what we're going to be doing, means to find the functions or the relations that produce the differential equation. So that's why it's sort of backwards from up here. So the idea up here is, in calculus, I give you this relation. You give me back this derivative thing. But now in differential equations, we go backwards. I give you this thing. You tell me where it came from. You tell me that this is where it came from, and then that means you've solved it. But it's a bit more tricky going that direction. And solving it means a bit more than what I just said, but that's okay for now. Okay, so let's see an example. So an example, just to show you, it can be much different than what I just said. So you could be given something like this. It just has to relate the variables and the derivatives. So something like this is a perfectly good differential equation. And it's a much harder looking, but we would want to try to do the same thing. We want to find the function or the relation solving this equation. So at a glance, this seems like very impossible, but we should just try to understand what this is saying. So this is saying, like, I have some function or perhaps relation, I don't know, but what I do know is if I take its change in y with respect to x, its derivative, find the derivative of y with respect to x, then when I multiply to x and I add it to the x times the y variable, then that'll all for some reason turn out to be the function sine of x. So like you can't just like look at it and be like, oh, I know the function that does this, or the relation that does this. It's much harder. Okay, so some are easier, some are harder. So not to fear, we're going to do easier ones first. So this is another differential equation that's much easier to look at. And this one you might be able to solve actually. So if I know that the derivative of y with respect to x is 4 times x, then luckily earlier I computed a derivative that created this, but there's actually many more. So for example, 2x squared plus 10, this solves the differential equation because if I find dy dx by using my rules, I will end up with the same thing. So this function solves the differential equation. But notice that there's actually more than one solution. There's many solutions. So does, what if I used 2x squared plus 17? That would work too. The key being that the derivative of a constant is 0. So if I change this to a 17, it would still work. Okay, so that differential equation, I didn't really show you how to solve it, but I showed you how to see that this was a solution. So I guessed the correct solution and saw that it worked. So another example, coming from what we just did, if I know that the change in y with respect to x, the derivative of y with respect to x is equal to the variable x divided by y, and it's negative, then I also know some solutions to this differential equation. And that's because I just used implicit differentiation to create this same relationship. But that's not the only one that solves it. So does this, or actually you could put any number you want on the right there. 1002, I don't know, whatever your favorite number is. And it's because if I apply the ddx to both sides, I'm going to, of the relation, I am going to create this differential equation just by solving the same way as I did last time. I'll get the same thing. So this produces this, the same relationship. Okay, so in general, this is how you check something as a solution. So in general, to check if something solves a DE, what you need to do, we need to find the appropriate derivatives and plug them in. And you should compare this to algebra. So in algebra, something like solving something like this, at one point in your life maybe seemed impossible. X squared minus 9 equals 0. And so you had to like learn a technique to solve it. But before you did that, you learned to check if something was a solution. And how did you do that? You just plugged it in. And if it worked, then yay, it's a solution. If it didn't work, then no, it was not a solution. That'd be bad. So in differential equations, same thing. Before we learn to solve, we learn to check. And so let's do that with a slightly harder example. So check if, okay, so at this point, I'm going to switch from f of x to y of x. This is something in this class that people like to use. Instead of f of x, they like to use y of x to really reinforce that y is dependent on x. The problem is it also looks like you're doing y times x, so it's really bad notation, but we got to get used to it. So I'm just going to throw it in now. So instead of calling it f of x, I'm calling it y of x. And we're going to check if this is a solution to y double prime plus 4y equals 0. Okay, so first thing into checking is we need to find the necessary things to plug in. So my differential equation here has a second derivative in it. And notice, again, I'm not writing y of x double prime because then it just gets too confusing. So I'm just writing y double prime. But it does mean the function in this situation because I do have a function. Okay, so let's find y double prime. Well, we've got to remember our derivatives of trig functions. So I am not going to spend too much time reviewing this kind of stuff. So you do have to go remember it yourself. So the derivative of cosine is negative sine. Use the chain rule. And then the second derivative, derivative of cosine is negative sine. Use the chain rule. Derivative of sine is cosine. Use the chain rule. Oops, first time should have been a sine. That's okay. Okay, so that's my first and second derivative. When I'm actually plugging it in, my differential equation only has a second derivative in it. So I'm not going to need the first derivative, but that's okay. I needed it to get to the second derivative. All right, so let's plug it in. Y double prime plus 4y becomes negative 12 sine of 2x minus 16 cosine of 2x plus 4 times, what was y? It was this thing up here, 3 sine of 2x plus 4 cosine of 2x. Great. Distribute, and everything should work out. So I get 12 sine of 2x and 16 cosine of 2x. Aha, everything will cancel out to be 0, which is what I wanted it to be. So I get 0 plus 0, which is 0. So yes, this y of x does solve the equation because this happened. So this is a solution. Great. Okay, so you should also see when things are not a solution. What does that mean? Because that can also happen. So not everything solves everything, but let's see. So if this, let's check if this guy is a solution to y double prime plus 4y prime equals 0. So slightly different differential equation than last time. And the answer will be no, but let's see. So I need y prime, which is 2x, and I also need y double prime, which is 2. So notice I am getting a bit lazier, so I'm not writing y prime of x, I'm just writing y prime, but that's okay. It means the same thing. All right, so now we got to plug it in, and I'll get 2 plus 4 times 2x, which is 2 plus 8x, which is not the same as 0. So not a solution. However, if x happened to be negative 1/4, then we would get 0 equals 0. But that's not good enough. It's not always true. So it's not a solution. Okay. So this thing that we get needs to equal this thing. They have to be the same. They can't just equal each other sometimes. So that's why it's not a solution. All right. Okay, so now that was with functions. Now let's go back to relations again. So a solution, which is a relation as opposed to a function, is called an implicit solution. And it goes with the word implicit differentiation, so that's good. Because typically no, never mind. Okay, so, well, if you do implicit differentiation, you're always doing it on an implicit solution. Okay, so let's do it. Let's check if this thing, which is a relation, is an implicit solution to differential equation y times dy dx equals negative x. So the word implicit is in opposition to the word explicit. So if it's a function, it's called an explicit solution, but you usually just say solution. You don't really care about saying explicit. Okay. So these work the same as in terms of checking, but now I have to find dy dx using implicit differentiation instead. So now defined, because I still need to plug it in, and I could have also called this y prime, same thing. But now to find y prime or dy dx, I have to use different implicit differentiation. Okay, so let's do that on the relation that I'm checking if it's a solution. So on this thing. Okay, so it should be very familiar by now because it's the same one that I've been using. And what you'll end up getting is that dy dx equals negative x over y again. Okay, I'll save some time. And then I'll plug it in to the differential equation to see if this is true. Okay, so y times dy dx becomes y times negative x over y. Y's will cancel and I get negative x. So yes, that's what I wanted to get. Y times dy over dx equals negative x. So this thing is a solution because it worked. I got negative x equals negative x. The same thing on both sides. Great. So one interesting thing was with this implicit solution. This doesn't always happen, but in this situation, you can get two explicit solutions. So that just means functions as opposed to relations from the implicit solution. By solving for y in two ways. So if I start with x squared plus y squared equals 25, then if I solve for y, there's actually two functions that I can use instead of one. And so I get these two different functions. So you can go ahead and try to solve for y, and you'll get these two things. When you square root, you get a choice of which one you want to pick. So that's why you get two solutions. But this cannot always be done. So don't always try to do this or anything. There's nothing wrong with an implicit solution. So if you solve the differential equation and you've got this as your answer, that would be fine. It's not necessary to try to create explicit solutions from that implicit one. Okay. So today is just about checking solutions. So that's what we did. But of course, we're going to learn how to actually do some techniques. So we'll first learn next time some techniques to solve some, let me emphasize, some types of differential equations. And I just have to call these ordinary differential equations just this once. So an ordinary differential equation is a differential equation relating derivatives and variables as opposed to partial derivatives. So we're not going to deal with those. Maybe much later we will. But for now, ordinary differential equations. But I'm mostly just going to call them differential equations because I don't want to say that every time. So equations involving derivatives and variables, we're going to learn some techniques to solve some types, because the whole point is in math, when you learn about something fancy, your big goal, of course, is like, I want to solve all of these things, but then that turns out to be too hard. So you like narrow your focus down and you learn some techniques that do some of them instead. So that's what we're going to do first. Okay, see you next time.